Okay, and this is the last thing we talked in the previous lesson. So magnet, in fact, we defined what a magnet is. We define what a magnetic material is. We define what non-magnetic material is. We know about them. And later we talk about that magnets have magnetic field lines around in the space around themselves. And these magnetic field lines form closed loops. And when you look at the shape, you cannot see any direction for magnetic field lines, but magnetic field is a vector quantity we need to determine a direction conventionally, and we determine that direction by putting a compass around the magnet. When you locate a compass, the compass direction will show you the direction of magnetic field at that point. Just like this, when I put a compass in here, as you see, N pole, which is the red side of the compass, points in that direction. So magnetic field indeed that point is indicated by the direction of the compass. For another point, if you choose another point in here, so compass direction will show you again what is the direction of magnetic field. Put different compass and several compass around this magnet, and then this compass will align themselves in the same direction of the magnetic field around this magnet. And this figure shows you that magnetic field lines seems to be leaving from N pole and entering to S pole in the outside. However, these magnetic field lines form a closed loop. They seems to be traveling from S pole to the N pole within the magnet, which means inside. And one pole is the north pole of this magnet, which is the magnetic field seems to be leaving, but other pole is the S pole of the magnet. The magnetic field line seems to be entering. So every magnet has two poles, N pole and S poles. And compass is important because in magnetic fields, we determine the direction of the magnetic field by a compass. Now I am going to define what is compass, what is that thing. Compass, in fact, consists of a very tiny magnet, very small magnet. That small thing is a magnet. Generally, magnets are polished by red, and the N pole of a magnet is polished by red. S pole is generally polished by blue or white. So this compass, that tiny magnet, is used to determine the direction of the magnetic field at every point. That tiny magnet sometimes called as needle, because it's so small, that's why it's called needle of the compass. So as I said, compass is a small magnet. Of course, like every magnet, compass needle will have also its own magnetic field. If this is the S pole, which is the white, which is the north pole N, and we know that every magnet has a magnetic field within from S pole to the N pole inside the magnet. So as these blue lines are representing the magnetic field lines within this compass in that direction. What happens then if we put this compass inside a magnetic field? Now I am going to put this compass inside that magnetic field. I gave direction of the magnetic field from left to right in that direction. What happens if I put this compass inside this magnetic field? So if you locate a compass inside a magnetic field, this compass will start rotating. It will start rotating until the magnetic field lines of the compass will be in the same direction of that external magnetic field. These red lines are representing external magnetic field. Those blue lines are representing the magnetic field of the compass. These magnetic fields must be in the same direction, which means this compass cannot stay stable at this position. It will turn until the magnetic field lines of the and external magnetic field will be in the same direction. This is what I said in the previous slide. N pole of the compass, as you see, N pole is this pole, sorry, N pole of the compass always points in the same direction of the external magnetic field. External magnetic field is right, as you see, N pole is also pointing to right. And that's why we use the compass to determine the direction of the magnetic field at any point in the space. You are just going to look at a compass at that point and you will see in which direction the compass is deflecting. That direction will tell you, yes, here exists a magnetic field and direction of that magnetic field is in that direction. Maybe several magnets around a natural magnet. This is the natural magnet, as you see this bar one, but those tiny magnets are the compass needles. So this is how these compass needle align themselves around a natural magnet. So I'm going to show you this now by my camera also. This is a really, really good example. Now you are going to see me, if you can see me. Can you see me now?
Yes, teacher.
Okay, I cannot know if you see me or not. But now this is the bar magnet, what I am showing you, bar magnet. And I have a compass also. This is compass, this is tiny magnet. Now, when I was moving this compass around this magnet, see that how compass is changing direction. See it. So now I'm going to move it around the magnet. So you see the compass needle change direction continuously, is it? Can you see it?
Yes.
So this is indicating that around this magnet, the magnetic field is always changing direction. That's why this compass needle is also changing direction when you move around this bar magnet. So that's why compass is very helpful to understand the direction of the magnetic field at that point. And there is a sectional question. This question is first time asked question in this 2020. They asked this question as a ministry exam question first time. So there are several compass located around a bar magnet, as you see in here. So one compass is located at point A, another compass is located at B, C, D, E, and F. So which of the compass needle orientation in the figure might correctly describe the magnetic field at that point? It's asking the question. We know that magnetic field lines are leaving from N pole and entering to S pole. So then you are going to check that if the magnetic field lines are in the same direction of the compass needle. For example, right here, magnetic field is in that direction. So, but compass needle shows in the opposite direction in D. If you look at D, magnetic field direction and compass needles are opposite. So this is impossible. Compass needle never stays in opposite. It will turn until needle points in the same direction of the magnetic field. So C, compass needle seems to be perpendicular to the external magnetic field. This is also not possible. But D, compass needle is to the left, magnetic field line is also to the left. This is possible. Correct. Correct one. In A, so compass needle and magnetic field lines are all seems to be in the same direction as well. In A, this might also be correct because question says might. I mean, it can be a little, we cannot know exactly. I mean, they are in the same direction, but seems to be in the same direction in A. But F, as you see, magnetic field is from N to S, but compass is in the opposite direction in F. F is not possible. And in E, as you see, magnetic field is from right to left, but compass needle makes an angle magnetic field. This is also not possible. So possible answers are B and A. So compass needle and external magnetic field must be in the same direction. So A and B are correct in here. And this is all about this question. And magnetic field, now we will define magnetic field a little in detail. First, it's a vector quantity. Magnetic field is a vector quantity. We should keep this in our mind. That's why we are going to have different directions in here. Also represented by B. B is the symbol of magnetic field. Unit of magnetic field is Tesla, Nikola Tesla. Maybe you heard that name because in the honor of Nikola Tesla, that unit is given. Unit of magnetic field is
Teacher?
Yes.
It's a unit and it's a quantity, so we can measure it, and it's a number.
Say again.
It's a number?
I mean, magnetic field is a number, of course. It is a number. It's a magnitude. Every physical vector quantity has a magnitude and also a direction.
I thought it was only an area around magnets, a field, not a
field. Yeah, field has a strength. Now I'm just going to explain in this picture. Field has a strength. Also, magnetic field is a direction. So magnetic field is stronger. Yeah, the strength is greater, more intense, where magnetic field lines are closer. Or magnetic field is weaker or less intensity, where the magnetic field lines are farther. Now tell me, where seems to be magnetic field lines closer? Where?
A. Near
A.
poles.
Poles are closer. Yani, when the magnetic field lines are closer to each other, yani more intense, we say that magnetic field at that point is greater. We are measuring how intense the magnetic field lines are by the magnitude of the magnetic field. So weaker, whereas the magnetic field lines are less intense. That's why in here, in A magnetic field, at the poles, magnetic field is the greatest. Magnitude of the magnetic field is strongest at the poles. But it gets weaker when you move away from a magnet because lines are getting farther and farther when you move away. So that's why we can say that magnetic field in here, according to this picture, strongest at point A, yani greatest in magnitude at point A, weaker at B, but weakest at point C. We got it. Magnetic field is a vector quantity represented by B. Its unit is Tesla. And when the lines are closer to each other, we say that magnetic field is strongest, closest, strongest, a little farther, weaker, and then farthest magnetic field lines, weakest. So that's why if we put the magnetic fields in here in order, magnetic field at point A is greater than magnetic field at point B, greater than magnetic field at point C. And it's a vector quantity, and we are going to study with the directions in this chapter, especially. Now, first, I'm going to define you, and many of you maybe don't know about this. What does plane mean? Because we will talk about the plane so much in this chapter 5. So I'm going to show you by the camera as well. Vertical plane and horizontal plane, what does it mean? So I have in my hand a file. So now there are two planes in this file, as you see. One plane is this one. So according to your camera, this plane is called a horizontal plane. But that one is vertical plane. Horizontal and vertical. But if a plane makes an angle like this, if it makes an angle, it's not horizontal, it's not vertical, it's called inclined plane. So horizontal plane, I am holding according to your camera, vertical plane or inclined plane. So about vertical plane and horizontal plane, we will talk so much that's why you should know what does plane mean. Plane is a surface. If that surface is horizontal, so we are going to say that surface is a horizontal plane. If that surface is vertical, we are going to say that it's the vertical plane. But if it is inclined, making an angle, so we are going to say already we said inclined plane. So then let's continue. If a magnetic field is in the plane of the plane of the page, we are talking about your book or notebook. You are going to put your notebook on the table. So the whole surface of this book or notebook, we are going to say plane of the page. This is plane of the page. If magnetic field is in the plane of the page, yani parallel to the plane of the page, and it can go in this direction, it can go that direction, to the right, to the left. We are going to define magnetic field like this. If magnetic field goes in that direction, parallel to the plane of the page, but to the top of the page, we are going to say it up to the plane of the page. This is up to the plane of the page. Can you see me?
We can't see the file. Like
you can't see the file?
Yeah, it's just your hand.
Okay, let me show it. Now, can you see it now?
Yeah, it's better. Thank you.
Okay, this is the top. Assume that this is the top of my file, top. So if the magnetic field lines are like this, so we say that magnetic field is up to the plane of the page. But if the magnetic field is to the bottom of the file, or to the bottom of your book or notebook, we are going to say it down to the plane of the page, down to the plane of the page. If the magnetic field is to the right of the page, we will say it to the, let's start from the left. If it is to the left, so it is to the left of the page, to the left in the plane of the page, or to the right in the plane of the page. So up to the plane of the page, down to the plane of the page, to the left of the page, to the right of the page. Okay, you got these directions? Clear?
Yes.
Yeah.
Evet, ses vermezseniz anlamayacağım. Bir ses verin, tamam mı? Okay, this is the first one. If the magnetic field lines are in the plane of the page like this, what if magnetic field is coming like that, like my pen? This magnetic field, this pen is now perpendicular to the plane of the page. This pen is now perpendicular to plane of the page. Then I will say that magnetic field, if you hold it like this, if the magnetic field ends are like this pen, so magnetic field is perpendicular to plane of the page. Assume that there are several pens, all are like this, perpendicular to the plane of the page. In this case, we have two directions. One of them is this pen, this magnetic field can go into the page, into the page. This is called into the page. You see the direction now? I mean the pen, how pen is entering, it's going into the page. One of them is this. Magnetic field is into the page. When it is into, you are going to think like something is moving away from you. Into the page, moving away from you, like an arrow. You throw an arrow. Remember dart example? You throw a dart. So when you look behind the dart, you see a cross sign. I mean, the back of the dart. Same thing is given in here. If magnetic field is into the page, we are seeing the back of the arrow, which is cross. That's why magnetic field is represented by cross if it is into the page. Got it? This one. It is going into. So I see only the back of the page, which is cross. However, if magnetic field is coming out like this, now I will enter from here. Now I am seeing tip of the arrow, tip of the pen. So if it is out of the page in that direction, we are going to say that, so this is dot. Only I see the tip of the arrow, it seems to be like a dot. So into the page is represented by cross, but out of the page is represented by a. If it is okay, I will continue with one more subtitle, magnetic flux. First, know that magnetic flux is not about chapter 5, in fact. This title will be used in chapter 6 mostly, but it is put in this section. Normally, I have several times planned to put it in chapter 6, but I mean, later I said, okay, let's go with this one. Only we'll learn this magnetic flux in here, and we will not use it in chapter 5 anymore. In chapter 6, we will use it's very important for chapter 6. What is magnetic flux? Now let's get first is total number of magnetic field lines that crosses a given area is called magnetic flux. Yeah, you are going to count how many lines are crossing this area now. We can count them. I will count them. So now I will count first line. Okay, just wait a little. Let me start counting them. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In here, 11 lines are crossing this area. Then we are saying that magnetic flux through this area is 11 Weber. Yes, Weber is the unit of magnetic flux. And symbol of the magnetic flux is phi. Phi. We are writing like this. It is written by phi. Magnetic flux. Its unit is Weber. Weber is the unit of magnetic flux. Is it okay? What magnetic flux definition is?
Yes, teacher.
We are going to count the magnetic field lines. How many lines are crossing an area? That number of lines will give us magnetic flux through that area. Symbol is phi, unit is Weber. So, but magnetic field intensity depends on 3 factors. One of them is, of course, magnetic flux depends on 3 factors. One of them is magnetic field intensity. Tell me, B1 or B2, which one is more intense?
B1.
Because lines are closer, is it?
Yeah, and they're more.
So B1 is greater than B2. Then count, I keep the areas same area constant. I only change the magnetic field intensity. B1 is greater than B2. Then magnetic flux, through which area number of lines crossing the area is greater? First or second? First one. First one, yes. First one has more intense magnetic field. Second one is less intense magnetic field. So first one, because the magnetic field is greater, more intense in the first one, magnetic flux also more intense in the first one. Yeah, magnetic flux is greater in the first one than the second one. So that's why we say that magnetic flux is proportional to magnetic field intensity. More intense magnetic field, so produce a greater magnetic flux.
Teacher, the
Yes.
only way to make magnetic field intensity like greater is just by making the lines closer, right?
Yes, that's all. Yeah.
Oh.
Or we draw it like this. If there is an intense magnetic field, we should draw the lines closer. And second factor, area. Now I put 2 areas in here, but I keep magnetic field constant. Everywhere magnetic field is constant because I draw them at equal distances, the lines. But one area is larger than the other one. Which area is larger?
A1.
So that's why A1 will have a greater magnetic flux. Count them. A1 will have 1, 2, 3, 4, 5, 6, 7 lines, but A2, 1, 2, 3, 4. So which means magnetic flux is also proportional to area. So then I can say that yes, magnetic flux is proportional to area of the surface. Proportional to magnetic field intensity, also proportional to area of the surface. And there is one more quantity which determines the magnetic flux, orientation of the surface with respect to magnetic field lines. So there are 2 cases. 2 of them I will talk about first. When the surface is perpendicular to magnetic field lines, so in here, greatest number of field lines crosses the area. Greatest maximum number of field lines crosses the area when the surface is perpendicular to magnetic field lines. So this one in here, magnetic flux is maximum, and this magnetic flux is calculated by multiplication of area of the surface, yani this area, multiplied by magnetic field intensity. We will multiply these 2 and we will get magnetic flux through this area. But If the surface is parallel to the magnetic field lines, if parallel, think that there is a sheet in your hand, a piece of, the paper. So you keep this paper parallel to these lines. Is it possible these lines to cross the surface of this page?
No.
Is it possible?
No.
No. If no lines crosses the area in here, because all the lines are parallel to the plane, if parallel to the page, so these lines cannot cross the surface of the page. In this case, so no magnetic field line crosses the area of the surface. That's why magnetic flux becomes zero. When the surface is parallel to the magnetic field lines, we are going to say that magnetic flux becomes, who said maximum? Minimum. And zero. Zero. Magnetic flux becomes zero when surface is parallel to magnetic field lines.
Teacher, it can be parallel vertically and horizontally too, right?
Possible, of course. Yeah, I kept in here horizontal to make a perspective. In vertical, sometimes it's becoming a little confusion for students, but I gave here a perspective. As you see, it is horizontal page. Magnetic field lines are to the right. You can also keep it like this. Your lines are like this, but you hold the page just parallel like that.
Yeah, that's what I meant.
It's also possible. Whenever the surface is parallel to magnetic field lines, so you are going to say that no lines crosses this surface. That's why magnetic flux becomes zero.
Yes.
This one we are going to use mostly. A. When the surface is perpendicular to magnetic field lines, we calculate magnetic flux by multiplication of A and B. When the surface makes an angle, tilt, in some Kurdish malzeme it's written tilt, makes an angle inclined to the magnetic field lines, just like this. So in this case, still there are lines crossing the area, but less number of lines than perpendicular. So magnetic flux becomes less than maximum because when it is perpendicular, so maximum number of magnetic field lines crosses the area. When it is parallel, zero. But when inclined, it becomes between maximum and zero. So magnetic flux becomes less than maximum, but more than zero. In here now, we are going to calculate magnetic flux by equation. AB cosine theta. You know what A is. A is the area of this surface. How much is this area? B is the magnetic field intensity. But theta is the angle between the normal of the surface and magnetic field lines. All right, I think you are able to see me now. So this is the surface. And this surface is now, can you see me now correctly? Clearly?
Yes.
Yes, teacher.
Okay, this pen now perpendicular to this surface. I am holding this pen perpendicular to this surface. This pen is the normal of this surface. So if surface is like this pen now perpendicular to surface. And normal of the surface is this pen. Any line perpendicular to the surface is called normal of that surface. In the 10th grade, when you are studying the mirrors and the lenses, maybe you remember that you should draw a perpendicular and to draw the law of reflection. So incoming light makes an angle with the normal, same angle with the reflected ray, something like this in the reflection rules, you'll learn about that. So then in this equation, in this magnetic flux equation, that angle is the angle between the normal of the surface and magnetic field lines. This normal is perpendicular to the surface, and you are going to get the angle between the normal and the magnetic field lines, which theta. We are going to use this very few times, not so much, but this is the equation to calculate the magnetic flux, AB cosine theta. So now let's study the cases. When the surface is perpendicular to the magnetic field lines, what is the theta? What is theta? When the surface is perpendicular to magnetic field lines, what is theta? What do you say?
Magnetic field?
So in here, surface is perpendicular, correct? Normal is this. This is normal line. What is angle between normal line and the magnetic field lines? Any answer?
Teacher, in the first one,
Yes, this one.
isn't it 90?
Is it 90? I mean, this green line and the red line, are they, what
There
is
isn't
angle
any
between?
angle.
What is the angle between them?
0.
0.
0 or 180. If they're in opposite direction, 180. If they're in the same direction, 0. Correct? If two lines are in the same direction, angle between them is 0. If two lines are in opposite direction, angle between them is 180. So in mathematics, you should learn about this before. So cosine 0 is what? Cosine 0 is what?
1.
1.
Cosine 0 is 1. When perpendicular, it is maximum, as you see, because cosine gets maximum value. In your equation, this magnetic flux equation, when the surface is perpendicular to the magnetic field lines, theta becomes 0 or 180, no matter. In all cases, it is cosine theta is 1 or -1, so magnetic flux gets the maximum magnitude. But when it is parallel, now think about this case. When the surface is parallel, this is normal. Is it? Now let me draw with another color. This is normal. What is angle between the magnetic field lines and the normal?
90.
What is cosine 90?
0.
0.
That's why magnetic flux is 0. So this equation also tells you at what angle magnetic flux is 0, at what angle it is maximum, at what angle it is greater, at what angle it is smaller. AB cosine theta is the equation for calculating magnetic flux. In our cases, most of the problems will be the surface will be perpendicular. We are just going to use the A times B because the cosine theta will be 0. When cosine theta is 0, when theta is 0, cosine gets 1. So magnetic flux is calculated by A times B. So this theta is the angle between the magnetic field lines and the normal of the surface. And note that normal of the surface is a perpendicular line to a surface. It's called normal of that surface. I explained that one. Any line which is perpendicular to a surface is called normal of that surface. And a new thing, less important, but it is included in the book. Area is a vector quantity. Until now, maybe you didn't hear about it. Did you know about this? Area is a vector quantity? Or did you hear the first time?
No.
First.
First time. Now, yes, area is a vector quantity because area has a direction. Because remember, vector quantity is the direction. Is it now? I am going to show by camera. Now I have a box in my hand. Let me. So you see the box in my hand?
Yes.
Okay, this box has surfaces, upper surface, near surface, front, back. Each surface has a direction. For example, this surface is looking up. That surface is looking to you. So this surface is looking to the right. That's left looking to the left. Below, bottom is looking down. So each surface is looking in a different direction. For that as an area, it's a vector quantity. So this is looking up. This is looking to the computer, to you. That is looking to me. This one to the right, this one is to the left. Bottom side and that looking down. So that's why area is a vector quantity. And what is direction of the area in this case? What is direction? Tell me. This surface is looking up. What is direction? Direction is the normal. Normal is looking up. This surface is looking to you. So what is this pen indicates? It is the normal. Normal is the direction of the area. This surface is looking to the right. So if when I put a pen perpendicular, it's to the right. Normal of this surface. Normal of, yeah, that's why normal of a surface, in fact, indicating the direction of that surface. So that's why in your book, this is explained like this. Yes, area is a vector quantity whose direction is the normal of the surface. In here, for example, let me switch off my camera. Okay, in here, this normal is looking to the right. So direction of this surface is to the right. This surface normal is looking to the up. So then direction is up. This surface is looking, normal is looking in this direction. So that each normal in here is representing the direction of that area. So area is a vector whose direction is the normal of the surface and whose magnitude is the measure of the area. And how many meters squared? How many centimeters squared? That is the magnitude of the area. As I said, this is less important, but it is in the book. That's why I have to explain this one. Yes, area is a vector quantity. Each area has a different side face, up, down, right, left, forward, backward. And any normal line drawn to the surface is representing the direction of the surface. And one more thing, in your book written, magnetic flux can also be represented by scalar product of area vector and magnetic field vector. So magnetic flux is a scalar quantity. Scalar quantity. Because it is the multiplication of these two vectors, but scalar product. In mathematics calculus, there are two different products. One of them is known as scalar product. The other one is known as vector product. For example, in the 11th grade, you learned about the work. Work is equal to force dot displacement. This is a scalar product. That's why you calculated the work as a scalar. But in the 11th grade, we learned torque. Torque is force cross distance. In here, torque is a vector product. In fact, all are in multiplication, but in calculus, in a little advanced mathematics, these operations are given different names. One of them is the scalar product. The other one is vector product. That's why magnetic flux is scalar product of area vector and magnetic field vector. This is just a representation. You are not going to make any calculation with this one. Just says you that, yes, magnetic flux is the scalar product of area vector and magnetic field vector. That's why result of is the magnetic flux. Magnetic flux is a scalar quantity.